So, now the next one is about phosphorus. So, it comes mostly in the form of phosphates from the coke and little from flux and iron ore. So, silica promotes its reduction in an indirect way. So, calcium phosphate reacts with silica, calcium silicate and P2O5, and which further reacts with carbon, which reduces the phosphorus and form the CO gas. So, most of the phosphorus reduction takes place in the hearth region. So, more than 90% phosphorus goes to iron and some is lost in the slag or flue gas. Phosphorus in the hot metal cannot be controlled in the blast furnace. Therefore, it has to be reduced during ore dressing operations or in the steel making process. So, because it cannot be controlled in the blast furnace, so ore dressing, that is processing of the raw material in the starting, should be taken care of to reduce the phosphorus. If that is not possible or it becomes expensive, in that case in the steel making operation it should be done, the phosphorus reduction. Another element which is there in iron is titanium. So, it comes from the iron ore mainly in the forms of ilmenite or rutile. So, ilmenite is FeTiO3 and TiO2 is rutile. So, in this form titanium comes to the metal. So, it is more stable than silica, therefore, its reduction even in the hearth is limited. So, hard to reduce at so this is the reaction which takes place mostly in the hearth region. So, carbon reacts with titanium oxide, gives titanium liquid and CO gas, and assuming the activity of carbon as 1, the equilibrium constant for this reaction can be written in this form. So, activity of titanium PCO square divided by activity of TiO2. So, log of it, and in terms of temperature the equilibrium constant is given in this. So, it is amphoteric in nature and reduces the fluidity of the hot metal as its content increases. So, it is not advisable to have more titanium in the ore or in the metal. So, it is mostly due to the formation of titanium carbide and titanium nitride. So, fluidity actually is reduces due to the formation of these carbide and nitride, and which can be formed with the dissolved titanium, react with carbon, gives you titanium carbide, and similarly titanium nitride, the free energy standard is given for this reaction is this. And because titanium carbide and titanium nitride have a very low solubility in the metal, they separate out to form incrustations on the hearth wall and the hearth bottom, and thus decreasing the available volume of the hearth. So, that creates also the problem in the hearth. So, it should be removed as much as possible. However, the content of titanium in the ore usually is low. So, reduction of titanium is intimately connected with the reduction of silica also, which is as follows. So, titanium oxide with silicon metal can be reduced to titanium and silica, and equilibrium constant for the reaction is given with this. So, activity of titanium, the activity of SiO2 and activity of TiO2 and activity of silicon. So, with this equilibrium constant one can know about the partition of this metal. Another reaction in the bottom part of the earth is occurred. This is carbon reacting with oxygen in the TiO region. So, that is the CO equilibrium. Of course, we have discussed about this in detail in Stake region, but now because we are talking about the lower part of the blast furnace, so we again are touching upon this. So, CO equilibrium, so at TiO carbon react with oxygen producing CO2, which then reacts with excess carbon further to produce CO, and the overall reaction can be given as carbon plus oxygen equal to 2CO. If you remember when we were talking about the combustion zone in the raceway, we talked about this reaction that in front of the TiO oxygen is in excess amount. So, carbon dioxide is formed which is like a oxidizing atmosphere there, but as soon as it reaches near the raceway boundary where more carbon is available, it is reduced to CO, and this is essentially about that reaction. And now this CO goes up and it comes in contact with iron ore in the form of wustite. As you remember, we mentioned near the cohesive zone, at the formation of the cohesive zone, melting of the ore and gangue starts. So, it makes a low eutectic solid. So, it start melting at the upper boundary of the cohesive zone and lower boundary of the cohesive zone, it becomes or liquid. And in that one, most of the quantity of iron is in FeO form, not in any other oxide, and of course, the remaining bit some liquid iron. So, this CO, when it comes in contact and with this FeO, which is dripping down from the cohesive zone into the dropping zone, it reduces iron according to this reaction. So, FeO plus CO gives you iron plus CO2. And this so in this reaction what is happening, that CO2 is forming again. So, because in the lower part of the blast furnace, especially in the dripping zone, everything else in liquid form except the coke. So, plenty of carbon is available in that. So, this CO2 again comes in contact with the carbon and form CO. So, this cycle is repeated to reach the equilibrium. Due to the condition in the lower part of the blast furnace, this equilibrium is never reached. So, schematically it is shown in this figure. So, this is showing about the CO2 equilibrium in the lower part of the blast furnace. So, if you look at y axis is the change in standard free energy, it is a standard Ellingham diagram for the oxide and temperature on the x axis. So, preheated air blast from the TiO is entered somewhere at this temperature and keeps on increasing with the reaction. So, CO2 form and the CO2 also becomes high, but as soon as it comes in contact with the excess carbon, CO is formed, and CO is forming. This is a CO line, and then now CO is formed, but the CO comes in contact with the wustite FeO. So, it reduces the iron. So, CO2 content increases further, and this line is showing CO2 ratio, but again this comes in contact with the carbon, CO is formed. So, this cycle keeps on repeating itself, and never, as you can see, it is never reached equilibrium, especially in the dropping zone or lower part of the blast furnace. So, this is about CO2 equilibrium, which we did not touch upon previously. So, we thought we will just talk a little bit about this one. Now, we will switch on to some other part, so which is about the liquid slag and melt. But before going to that, we would like to have some physico-chemical properties of melt. So, we have a liquid iron. So, the phase transformation of pure iron occurs as alpha ion, you must be aware of that. So, body center cubic center. So, body center cubic at 900 degree Celsius when temperature reaches is converted into gamma ion, and at 1537 degree Celsius it keep on heating, it converts into liquid iron. So, this is the melting point of the iron, and if you heat it further, then at 2870 degree Celsius it becomes into vapor form or gaseous ion. So, this is for the pure iron. So, as you can see, melting point of pure iron is very high. So, it is really you cannot it is very difficult to achieve that sort of temperature throughout the furnace, in the blast furnace throughout of it. But however, for impure iron, liquidus temperature of this is decreased. So, this we will see the effect of impurities on the liquidus temperature. So, liquidus temperature, that is the temperature at which it completely melts or completely in liquid form. So, liquidus temperature of the iron alloy can be calculated as, so 1537, that is the actual melting point of iron, and if there is no impurities, that would be the liquidus temperature. However, if you have carbon or phosphorus, sulfur, copper, silicon, manganese, molybdenum, nickel, chromium, titanium or vanadium, all of these contribute in reducing the temperature. So, you can see if we have a 1 weight percent carbon, the liquidus temperature reduces to 1449 degree Celsius, and if it is 4 weight percent carbon, as you know in the blast furnace, mostly especially in lower part of the blast furnace or in the earth, lots of carbon. So, it is a carbon saturated melt. It reduces almost 1185 degree Celsius at 4 weight percent of carbon, the liquidus temperature of iron. So, this is the effect of alloying elements on the melting point of liquid iron, and one can calculate the liquidus temperature using this equation. Similarly, density of the iron varies with temperature, and this empirical correlation can be used with respect to temperature for density variation. And so, where T is in degree Celsius and iron density is given in gram per centimeter cube. So, at 1550 degree Celsius iron density is 7, at 1700 degree Celsius is 6.9. So, as the temperature goes up, start decreasing, and in the blast furnace, if you look at and we consider 4% carbon in iron, then the density of iron is about 6.75 at 1600 degrees Celsius. So, but roughly one can calculate the density of iron using this empirical correlation with respect to temperature. Similarly, the surface tension of the iron is of course surface tension varies with temperature. So, it is a function of temperature. So, it is given by this empirical correlation. So, surface tension of iron sigma F equal to 2367 minus 0.34 T, where T is the temperature in degree Kelvin, and the surface tension is given in this equation in Dien's per centimeter, which can be converted into MKH or SI unit Newton per meter into 10 to the power minus 3. So, most solutions do not have much effect on surface, most solutes, beg your pardon. So, most solutes do not have much effect on surface tension except sulfur, oxygen, tellurium and selenium. So, for example, 0.2% sulfur or 0.1% oxygen in iron lowers the surface tension by about 1100 between 1550 and 1600 degrees Celsius temperature. So, that is a big drop in the surface tension. So, these elements sulfur, oxygen, tellurium and selenium, they affect surface tension significantly. Another property of liquid iron is viscosity. So, viscosity again it is dependent on the composition, and mostly because carbon is more soluble in iron. So, this figure shows more about the dependence of viscosity in iron carbon melt with respect to temperature at various temperatures. So, viscosity in kg per meter second and temperature composition in terms of carbon percentage. So, you can see as the temperatures increases, or in fact increases, the viscosity is decreasing, and also with the percentage of carbon in present in the melt usually reduces the viscosity, which you can see in all these curve, that viscosity usually reduces after as the carbon percentage in the melt increases, but mostly between 1 and 2% it is similar, but as such from starting to and it keep on reducing. So, one can get the viscosity, density, surface tension and melting temperature of the liquid iron from these correlation or figures. Similarly, now a little bit about the slag, general properties of the slag. So, in iron making, calcium oxide or lime is added in the form of calcium carbonate. So, that is in the starting which we have said, and this really dissociates near the cohesive zone where temperature is about close to 1000 degrees Celsius. So, in the form of CaCO3 with the objective of fluxing acidic oxide like SiO2, Al2O3 etc. To form slag at reasonably low temperature, that is below 1300 degrees Celsius. Though this is still high, furtherly if you remember just now we discussed, if 4% carbon is present in pure iron, then this pure iron liquidation temperature reaches almost to 1200 degrees Celsius. Now, further liquidation temperature of the slag can be lowered by the addition of MgO and TiO2 and some other oxide. So, extensive physicochemical measurements have been carried out on molten slags, and it is found that basic building block in SiO2 and silicates is the silicon oxygen tetrahedron as shown in the figure in this one. So, you can see this is a sort of a tetrahedron basic block for silicates. So, 3 oxygen atom and silicon atom in the middle, and so this is a basic block of slags. However, this can be break down. Now, we will see how. So, upon melting pure SiO2, which is 3D crystalline network, short range order remains, but the long range order is destroyed. So, this you will see the chain, it just keep on extending and make a very long chain in that. So, that in silicon oxygen tetrahedron. So, that is the building block. So, which is a long chain in this form, but when you heat it up, it breaks down and form the short range order chain. So, long range order is destroyed. Oxide are ionic in both solid and liquid state, because this is oxide. So, this is in liquid state is in an ionic form. When you say ionic, certainly the ions are there in the slag. So, molten slags are polymeric ionic melt. The cation like calcium, sodium, iron, etc. are free and mobile, while anions, silicate, AlO4, etc. are complex and less mobile. So, these are freely movable, but these are less mobile, and basic oxides are network breaker. So, like CaO, MgO, these are basic oxides. So, these are network breaker. When we say network breaker, we are talking about the orders. So, you can see this is a long chain of silicon oxygen tetrahedron, and if you add basic oxide like CaO. So, before addition combined, when you add that, it breaks it, that chain. So, after addition of CaO, separate out and it leaves the cation and anionic charges on that, and that is how it becomes ionic melt in slag. So, these are network breakers, that is why it is known as basic oxide are network breakers, and acidic oxide like SiO2 are network formers. So, in the slag we have quite good amount of line. So, it is breaking the network, and which also then promoting the polymeric ionic melt. And if you remember this correctly, when we were talking about the sulphide capacity, we had written down the equation in form of in the ionic form, which is mostly due to this region. So, therefore, with the addition of more and more metal oxides like MO to SiO2, there is a progressive breakdown of silica network, and excess oxygen of metal oxide is expected to be present as free oxygen ion. So, through the ionization. So, MO equal to M plus 2 plus O minus 2. So, this is in the ionic form, and this is the equation which we used in defining the sulphide capacity. In fact, in steel making also similar ways you can write the equation for the phosphate capacity, another one which we have not discussed here, because that dephosphorization takes place more in the steel making operation. So, you again represent in ionic form. So, slag density does not vary much with composition and temperature, which is between 2500 and 2800 kg per meter cube. However, viscosity varies significantly with temperature and composition. So, as such it does not vary much the density, but the viscosity varies significantly, and which can be seen from all right, there is no figure, but viscosity varies significantly with temperature and composition.